Why the universe makes it impossible for civilizations to meet. Right now, at this very moment, there may be another civilization somewhere in this galaxy doing exactly what we do, turning instruments toward the sky, running calculations, building theories about the cosmos, and asking that one question that seems to follow intelligence wherever it emerges. Are we alone? The numbers, taken at face value, suggest we should have company. Work through the basic statistics of the Milky Way and the conclusion seems almost unavoidable. Hundreds of billions of stars, trillions of planets, billions of years of cosmic time. Chemistry that plays by identical rules everywhere matter exists. And yet, here we are, scanning the sky with the most sensitive instruments our civilization has ever built. And the sky gives nothing back. No signals, no visitors, no evidence that anything has ever looked back. That silence is one of the most profound facts about the universe we live in. And the explanation may not be that we're alone. The explanation may be something stranger and more unsettling, that the universe builds minds and then constructs walls between them that nothing can cross. Walls made not of stone or choice, but of the universe's own geometry, of distances, of physics, of time. Let's work through this carefully because the barriers are real, and understanding them changes everything about what the silence means. A galaxy full of possibilities. The Milky Way is home to roughly 400 billion stars. That number is difficult to feel in any genuine way. Written on a page, it looks manageable. But consider what it means physically. If you could visit one star per second, counting them all would take more than 12,000 years. The galaxy stretches so wide that light, the fastest thing in the universe, requires a full 100,000 years to travel from one edge to the other. It is not a neighborhood. It is a continent of fire, and we occupy one unremarkable corner of it. For most of human history, the planets in our own solar system were the only confirmed planets anyone had ever seen. The question of whether other stars had planets was entirely open. Some astronomers suspected they did. Others thought our solar system might be unusual, that most stars were simply lonely fires with nothing circling them. The silence of the sky seemed to support either possibility, and there was no way to tell. That uncertainty lasted until modern telescopes changed the picture entirely. Astronomers developed the capability to monitor distant stars with extraordinary precision, watching for the faint, repeating dimming that occurs when a planet crosses in front of its star. The signal is incredibly subtle, like a moth crossing briefly in front of a lamp miles away. But with enough patience and precision, it shows up clearly. And when astronomers began looking systematically, they didn't find a handful of planetary systems. They found planets essentially everywhere. Rocky worlds, gas giants, planets orbiting so close to their stars that their surfaces could be permanently molten. Planets so distant that their atmospheres may have frozen solid long ago. Planets circling two stars at once, entire systems packed with more worlds than our own. The variety was far beyond what anyone expected. The conclusion is hard to escape. Planets are not rare accessories attached to unusual stars. They are the normal product of star formation. When a star coalesces from a spinning cloud of gas and dust, the leftover material forms a disk, and from that disk, planets emerge almost automatically. The universe manufactures planets the same way it manufactures stars, relentlessly, as a standard byproduct of the same processes that govern matter everywhere. So there are hundreds of billions of stars in our galaxy alone, and most of them have planets. Even if only a modest percentage orbit in the right location with conditions that could allow liquid water on their surfaces, you're still counting candidate environments in the billions. Billions of places where sunlight, minerals, heat from a planet's interior, carbon compounds, and water might have operated together across enormously long timescales. This is where the story begins to feel genuinely hopeful. The ingredients and the conditions life, at least the kind we understand, requires a relatively short list of things. It needs chemistry rich enough to build large, complex molecules, the kind of carbon-based structures that can store information, catalyze reactions, and copy themselves. It needs energy to drive those reactions forward. And it needs a stable environment where these processes can persist and evolve across vast stretches of time. On Earth, liquid water has been central to all of this. Every living organism on the planet depends on it in some fundamental way. Water is the medium in which biological chemistry happens, the fluid inside cells, the solvent in which proteins fold and enzymes function. Its unusual physical properties make it nearly ideal for supporting complex chemistry. This is why astronomers focus so much attention on what they call the habitable zone, the range of distances from a star where a planet's surface temperature might allow liquid water to exist. Not so close that oceans boil off, not so far that water freezes permanently. The term sounds almost welcoming, but it's worth being precise. It's not a guarantee of life. It just means the temperature range under the right atmospheric conditions could permit liquid water to remain on the surface. But in a galaxy containing hundreds of billions of stars, could permit becomes an enormously powerful phrase. Even if only a modest fraction of stars have a rocky planet in the right temperature range, you're still counting candidate worlds in the billions. Billions of places where energy, water, minerals, and carbon compounds might have had billions of years to interact and experiment. The universe's chemistry reinforces this. Carbon, the essential backbone of all known biological molecules, is manufactured inside stars and scattered through the galaxy when those stars die. Oxygen, nitrogen, phosphorus, the elements that life on Earth relies on, all are products of stellar interiors, distributed across space by stellar death and gathered again into new generations of stars and planets. A carbon atom near a distant star obeys exactly the same laws as one on Earth. The universe doesn't reserve its chemistry for special locations. It distributes the raw materials of life across every region of the galaxy. Earth itself provides an important data point. Life appeared here very early. The planet formed about 4.5 billion years ago, and its first several hundred million years were violent and hostile. But once conditions stabilized and liquid water could persist, signs of life appeared surprisingly quickly by geological standards, within a few hundred million years of when Earth became habitable. One example isn't enough to prove that life is common, but the speed at which life appeared on Earth, combined with the sheer number of potentially suitable environments elsewhere, gives scientists reasonable grounds to take the possibility of alien life seriously, not as a certainty, but as a genuine likelihood worth investigating. The harder step, intelligence. Even if life is widespread in the galaxy, intelligence is a completely separate and much more difficult question. Earth has been alive for roughly 4 billion years. For most of that span, the planet was microbial. Bacteria dominated this world for the first 3 billion years of biological history. Complex multicellular life arrived late. Animals came later still. The specific branch of life that eventually produced humans appeared almost at the end of the story, in the final few percent of Earth's biological timeline. And the particular form of intelligence capable of technology, building radio transmitters, launching spacecraft, detecting signals from space, is younger still. Human technological civilization has existed for a few centuries. Against 4.5 billion years, that interval is essentially nothing. Intelligence may require an enormous additional chain of evolutionary conditions. The right pressures, the right timescales, the right absence of catastrophic extinctions at the wrong moments, and even then, A technological civilization is not guaranteed simply because a living world exists. Consider the most conservative possible estimate. Suppose only 10 technologically advanced civilizations exist in the Milky Way at this moment. Not millions, not thousands, just 10. That alone would represent one of the most profound truths ever discovered, that consciousness has independently emerged more than once, that intelligence is not a single bizarre accident but a pattern the universe is capable of producing. And yet even 10 civilizations distributed through the Milky Way would be separated by a geometry that makes contact almost inconceivably difficult. The first wall. Distance. 10 civilizations scattered randomly through the Milky Way would not be neighbors in any meaningful sense. Imagine spreading 10 grains of sand across a continent, and you've approximated the situation. The distances between them would be measured not in miles or kilometers, but in light years. The distance light travels in an entire year at 300,000 kilometers per second, and the gaps between randomly placed civilizations could easily reach thousands or tens of thousands of light years. What does that mean practically? A radio signal traveling at the speed of light, the absolute maximum velocity anything achieves, would take thousands of years to cross such a distance. A reply would take thousands more. What we might call communication becomes something else entirely. One civilization broadcasts into the dark. By the time the signal arrives at another civilization, the senders may have transformed beyond recognition. Their languages may be gone. Their civilization may have ended. The receiving civilization would not be hearing a neighbor speak. It would be reading a message from the deep past, from a civilization as it once was, not as it is. Physical travel is worse by every measure. Even if a spacecraft could move at a significant fraction of the speed of light, crossing thousands of light years would still take thousands of years. The crew who launched the ship would be long dead before it arrived. And here is what makes the distance problem so fundamental. There is no engineering solution that makes the distances shorter. There is a limit built into the universe itself. The second wall, the speed of light. Light moves at about 300,000 kilometers per second. In daily human experience, this is effectively instantaneous. Sunlight takes about 8 minutes to reach Earth. A beam of light could circle the planet more than 7 times in a single second. But the galaxy operates on different scales, and on those scales, even light is slow. The nearest star system, Alpha Centauri, is more than 4 light-years away. Light itself takes over 4 years to cross that distance. The center of the Milky Way is tens of thousands of light-years from Earth. The far edge of the galaxy is 100,000 light-years away. At the maximum speed the universe permits, crossing the Milky Way requires 100,000 years, 10 times the entire span of recorded human history. This speed limit is not a temporary engineering constraint that future technology will eventually overcome. It's written into the fundamental structure of space-time. As an object accelerates, the energy required to keep accelerating, it rises. At ordinary speeds, this increase is manageable. But as the object approaches the speed of light, the required energy doesn't rise linearly. It climbs toward infinity. To actually reach light speed, an object with mass would need an infinite supply of energy. That's not a practical limitation. It's an absolute one. Science fiction has long imagined warp drives, wormholes, and shortcuts through folded space that allow ships to sidestep this limit. These ideas are appealing because they answer a genuine emotional need, the desire to make the universe feel traversable. But in known physics, they remain speculative at best. Some solutions to general relativity allow for structures that might theoretically function as shortcuts. but they require conditions that have never been observed and may not exist. Imagination is not a propulsion system. Given realistic physics, the question becomes, what does it actually take to try to cross interstellar distances? The energy wall. Consider what even a small fraction of light speed requires. 1% of light speed sounds trivially small, but 1% of 300,000 kilometers per second is still 3,000 kilometers per second, vastly faster than any spacecraft humanity has ever built. At that speed, crossing 1 light year takes 100 years. Crossing 1,000 light years takes 100,000 years. 10% of light speed is more serious. At that velocity, 1,000 light years still takes 10,000 years. A civilization 5,000 light years away would require 50,000 years to reach. These aren't just long journeys. They're journeys longer than the entire span of human civilization on Earth. The energy required to reach even these fractions of light speed is staggering. This is where the physics of propulsion becomes its own barrier. A rocket moves by throwing mass backward, propellant, to push itself forward. The faster you want to go, the more propellant you need, but propellant itself has mass. Carrying more makes the ship heavier, which requires even more propellant to accelerate, which adds more mass. At low speeds, this is an engineering challenge. At interstellar speeds, it becomes something close to an impossible spiral. Chemical rockets are completely inadequate. The energy in chemical bonds is far too small. Nuclear fusion is far more energetic and could in principle push probes to significant fractions of light speed. Antimatter would be more powerful still. But antimatter doesn't exist in useful quantities, and producing it requires enormous energy inputs in the first place. And there's a problem easy to overlook. A ship must also decelerate at the destination. Arriving at another star while still moving at 10% of light speed isn't arrival. It's a flyby. To actually stop, enter orbit, and land requires nearly as much energy as the initial acceleration. The cost must be paid twice, once to leave, once to arrive. The universe doesn't offer discounts. The void itself. Even if the energy problem were somehow solved, interstellar space presents hazards that are easy to underestimate. The space between stars contains roughly 1 atom per cubic centimeter. 1 atom in a space the size of a sugar cube. This sounds peacefully sparse. But a spacecraft moving at even a fraction of light speed isn't drifting gently through this near vacuum. It's plowing through it at enormous velocity. At high speed, individual hydrogen atoms impact the front of the ship with significant energy. Across years or centuries of travel, this becomes continuous erosion, the ship worn down, atom by atom, by the medium it moves through. Cosmic rays add another layer of danger. These are high-energy particles accelerated by supernova explosions and other violent cosmic events. On Earth, we're shielded from most of them by the atmosphere and magnetic field. A spacecraft crossing interstellar space has no such protection. Radiation passes through metal, electronics, and biological tissue. It damages DNA, disrupts computer memory, and degrades materials over time. Shielding can help, but shielding has mass, and mass is never free. More shielding means more energy needed to accelerate, which makes everything harder. Then there is dust. Interstellar dust grains are sparse, but a ship crossing thousands of light years sweeps through such an enormous volume of space that even extremely rare hazards become probable over the length of the journey. At a fraction of light speed, even a microscopic grain carries kinetic energy comparable to a small explosive. Over thousands of years of travel, the probability of at least one catastrophic impact approaches certainty, and navigation across those distances adds yet another layer. Stars are not fixed. The Sun orbits the galactic center at roughly 230 kilometers per second. Every other star follows its own path. Over a human lifetime, these motions are barely perceptible. Over tens of thousands of years, a star can move many light years from where it was when a journey began. A ship launched toward a distant civilization must aim not at where the destination is, but at where it will be when the ship arrives. A prediction that grows less reliable the further into the future it projects. A small error in the initial trajectory, compounded over 50,000 years, could mean missing the destination entirely. The fourth wall. Time. Even if a civilization solved the energy requirements, survived the hazards of deep space, and navigated accurately across enormous distances, there is a fourth barrier that operates completely independently of all the others: the problem of time. The Milky Way is more than 13 billion years old. Civilizations are not permanent features of galaxies. They are events, brief arrangements of energy, organization, and knowledge that appear, persist for a while, and then either transform into something else or end. Our technological civilization has existed for a few centuries. Even if humanity survives for thousands of years, that's a thin slice compared to the billions of years the galaxy has been producing stars and planets. Two civilizations don't just have to exist in the same galaxy, they have to exist at the same time. Their windows of technological activity have to overlap, and those windows may be short compared to the timescales on which civilizations appear and vanish. Imagine a building with 1,000,000 rooms where each person is only awake for 1 hour every 1,000 years on no fixed schedule. The building isn't empty, people do exist. But finding someone awake at the same moment as you requires a coincidence so improbable that you might spend your entire life in the corridors without encountering anyone. The Milky Way may work the same way. Civilizations may have appeared and vanished across the full span of galactic history, with most never existing at the same moment as any other. Light makes this worse in a specific way. When you observe a distant star system, you don't see it as it is now. You see it as it was when the light left it. A civilization 10,000 light-years away appears to us as it was 10,000 years ago. If we received a signal from them today, we'd be reading a message from their past. A reply would take another 10,000 years to arrive. A single exchange of 2 messages would span 20,000 years, longer than the entire span of recorded human civilization. Physical travel stretches the problem further still. If a ship takes 50,000 years to reach another civilization, then the destination must remain intact and capable of receiving visitors for 50,000 years after the signal that prompted the journey was sent. The ship might launch toward a world filled with radio transmitters and cities, only to arrive above a planet that has returned to wilderness, been struck by catastrophe, or transformed into something unrecognizable. A civilization is not a mountain waiting at the end of a road. It's more like a flame, burning for a while, changing things around it, and eventually either transforming or going out. To reach another flame, you don't just need to know where it is. You need to arrive while it's still burning. The fifth wall, the expanding universe. Beyond all of the barriers within the Milky Way, there is one more that operates at an entirely different scale. And unlike the others, this one admits no exceptions and no solutions within known physics. The universe is expanding, not just at its edges, everywhere, in the sense that the space between distant galaxy clusters is continuously growing. Distant galaxies appear to be moving away from us, and the farther away they are, the faster they seem to recede. Crucially, this isn't like fragments flying outward through empty space. The galaxies aren't necessarily moving through space. Space itself is stretching between them, like dots drawn on an inflating balloon, moving apart not because any dot is traveling, but because the surface connecting them is growing. At nearby distances, gravity overcomes this expansion. That's why the Milky Way and Andromeda are moving toward each other rather than apart. But beyond a certain distance, expansion wins. The recession of distant galaxies accelerates, and because space itself is doing the expanding, the most distant regions can be carried away from us at rates exceeding the speed of light, not because any physical speed limit is violated, but because the space between us and those regions is growing faster than light can cross it. This creates a horizon made not of matter, but of geometry. Beyond a certain distance, light emitted today will never reach us. Not because it's too weak, not because anything blocks it, but because the space it has to traverse is expanding faster than it can close the gap. The photon moves forward at the maximum speed nature allows, but the distance ahead grows faster than it travels. For any civilization beyond this cosmological horizon, contact isn't merely difficult, it's geometrically impossible. No signal can cross, no ship can arrive. And this isn't going to change as technology improves, because the barrier isn't an engineering problem. It's a feature of how the universe is structured. The observable universe contains perhaps 2 trillion galaxies, each holding billions of stars, some fraction of which may host living worlds. A very large fraction of any civilizations that might exist in those galaxies are already beyond our cosmological horizon, in regions of space causally disconnected from us. Their ancient light may still be arriving from billions of years ago, but any message they sent today would never reach us. Any message we send would never reach them. There may be vast numbers of minds in those regions right now, asking the same questions we ask, arriving at beautiful answers to problems we haven't yet learned to formulate. And we will never know, not because our technology is insufficient, because the expansion of space has placed them permanently beyond reach. What the silence means. Given all of this, the sheer scale of distances, the speed limit embedded in physics, the energy requirements for interstellar travel, the hazards of crossing the void, the problem of temporal misalignment between civilizations, and the expanding geometry of space itself, the silence of the sky begins to look very different. The silence does not prove that the universe is empty. It does not mean Earth is the only place where atoms have organized themselves into something capable of curiosity. It may not even indicate that intelligent life is particularly rare. The silence may simply be what separation sounds like. Civilizations may exist across the galaxy. They may have built instruments, transmitted signals, developed theories about whether anything else is out there. Some may have searched their skies with the same mixture of mathematics and longing and still found only quiet. They may have drawn the same conclusion we fear, that no one is listening. And they may have been wrong in exactly the way we may be wrong. Not because the answer doesn't exist, but because the distances between questions and answers are so vast that contact remains impossible within any span of time that matters to a civilization. The universe may be full of answers that cannot arrive. There is a particular quality to this situation that takes time to absorb. It suggests a cosmos generous with the raw materials for life, distributing carbon, water, energy, and stable planetary environments across hundreds of billions of star systems, and yet structured so that the resulting minds remain permanently sealed from each other, not by choice, not by failure, by geometry. Some of this isolation comes from scale. The Milky Way is enormous. Even if it contains many civilizations, each may be so far from the others that no signal could bridge the gap within any civilization's window of existence. Some comes from time. The galaxy has been generating stars and planets for over 10 billion years, and civilizations have probably arisen and vanished throughout that entire span, with most never existing at the same moment as any other. Some comes from fundamental physics, the speed limit woven into space-time, and the expansion that carries distant regions permanently beyond reach. Together, these create a universe that may be far more populated than it appears, and yet profoundly, structurally unable to bring its inhabitants together. The search and what it means. None of this makes the search for other civilizations pointless. Understanding the barriers makes the question more interesting and any future discovery more significant. Humanity has already accomplished something remarkable. We have measured the scale of the galaxy we inhabit. We have detected planets around other stars and analyzed their atmospheric chemistry from across light years. We have launched spacecraft beyond the edge of the solar system. We have built instruments capable of listening for signals across interstellar distances. We have sent transmissions of our own into space, knowing they may travel for millions of years before encountering anything capable of detecting them. These aren't failures. They are acts of a civilization that has become aware of its situation and chosen to respond with curiosity rather than resignation. A radio signal leaving Earth doesn't need a reply to be meaningful. The act of sending it reflects something that didn't exist for most of cosmic history. Matter organized into a form capable of reaching outward into the darkness and attempting contact. For billions of years, the elements that make up living things were scattered through nebulae and stellar interiors, incapable of building anything or wondering about anything. The fact that on at least one world, around one ordinary star, those elements have assembled themselves into something that asks questions about the universe is not a trivial achievement. And if a signal from another civilization ever arrived, even the most minimal confirmation, even an unmistakably artificial pattern in the noise, it would transform our understanding of our place in the cosmos more profoundly than almost any other discovery in history. It would mean that the processes that produced us have produced others. That consciousness is not a unique accident, but a feature of the universe's capacity. That awareness is not alone. Even the persistent absence of any signal teaches us something real. It informs us about the shape of things, about how rare the right conditions might be, about how vast the separations are, about how the universe is actually arranged. What to do with the loneliness. There is a particular kind of loneliness in understanding all of this fully. Not the loneliness of an empty room, but the loneliness of recognizing that the universe may contain countless other minds, and that we may never encounter them. Not because we haven't tried, not because anyone has chosen silence, but because the laws of physics have arranged things in a way that makes meeting almost geometrically impossible. Two civilizations on opposite ends of the galaxy might independently discover the same laws of nature. They might measure the same fundamental constants, derive the same equations, reach the same conclusions about space-time and matter and energy. They might understand the same barriers that keep them apart. They might feel the same combination of awe and confinement when they grasp how enormous the universe is and how confined they are within it. In that sense, there may be a strange kinship between civilizations that have never communicated and never will. They share the same universe. They operate under the same rules. They encounter the same limits. And if they're doing science, they'll arrive at the same truths, including the truth about why they're separated. This doesn't dissolve the loneliness, but it reframes it. The walls between civilizations are not punishments. They're the same features of the universe that made the civilizations possible in the first place. The vast scales of space and time that allowed stars to burn, planets to cool, oceans to persist for billions of years, and evolution to run its long experiments with chemistry and complexity. What follows from all of this, for us, here, in our brief window, is something like a deepened sense of responsibility. If technological civilizations are rare, each one represents an extraordinary concentration of complexity in a universe that is mostly silent matter and energy. Every civilization that exists matters in ways that are hard to overstate. every one that collapses or allows itself to decline represents something lost that may have taken billions of years to produce. If civilizations are common but isolated, then the universe is running many parallel experiments, each developing its own understanding of reality, its own forms of knowledge and expression, its own answers to the questions that intelligence generates wherever it appears. Each experiment is sealed from the others. What any one of them discovers, creates, or loses is entirely its own. Either way, the implication is the same. What happens here matters. Not because someone is watching, not because other civilizations will know or care, but because this may be the only instance of this kind of awareness that this corner of the universe will ever produce. The universe may never allow two civilizations to stand face to face. It may keep them separated by distances that light takes thousands of years to cross, by timescales that dwarf the lifespans of civilizations, by energy requirements that make physical travel effectively prohibitive, and by an expanding geometry that places most of the universe permanently out of reach. But it has, on at least this one world, around this one ordinary star, produced something that can look up at the night sky, recognize the barriers, understand the loneliness, and choose to keep searching anyway. That choice, made with full knowledge of how vast the silence is and how unlikely any answer becomes, may be one of the most interesting things the universe has ever managed to do. Not that it makes meetings impossible, but that it produces beings who understand exactly why and look up into the dark regardless.